Okay, welcome everyone to the Dark Sky Project. My name is Olive. I am one of the astronomy guides here, and today we are going to talk about the Vera Rubin Observatory. Welcome in, guys. But before we get started on that, we are just going to start going over just a few of the house things that we have to. The first is just the health and safety. There is a fire exit either side for you guys, and if you need to leave the room at any point, if you need to just leave, you're more than welcome to do so just out the door that you guys came in. If you need to go to the toilet or anything like that, reception can always let you back into the room if the door gets locked as well. If you have any questions, please, of course, just let me know. I'll be stopping periodically as well to answer those questions, so no stress. But today, what we are going to do is focus on unlocking the cosmos. So we're going to talk about the Vera C. Rubin Observatory, which is one of our amazing new ground-based observatory telescopes that's hopefully going to start operations this year. And its main goal is going to be to create a 10-year time lapse of the southern hemisphere night sky. So that's the night sky we have here in Lake Tekapo, which is awesome. It contains so many wonders, and hopefully it's going to help us understand a few of the mysteries surrounding astronomy at the moment as well. So to get started, we are going to talk about the two main missions of the telescope. So these are the project missions, and this is what we're aiming to kind of do. So the first one is to build a well-understood system that will produce an unprecedented amount of data to study the deep and dynamic universe. Our second, to make data widely accessible to the diverse community and engage the public to explore the universe as well. So starting with that second one, the Rubin Observatory is set to make its data as publicly accessible as possible. And this is because there's going to be so much data. It's going to collect so much information that just a handful of scientists cannot solve all the mysteries with it. So it's going to be open to loads of universities working with schools. It'll become open to all of you guys after just a little bit of time. There'll be some of the best things as well is citizen science programs. So if you want to go home and get involved, there's these programs where you can look online, you can work with the data yourself, get results, and then give it in to the universities that are running it, and you'll help solve some of these mysteries. So have a look out for all of this. But what we're going to focus on today is kind of unpacking that first bullet point there, that first project mission. Because this is kind of what the observatory is doing. So it's going to build a well-understood system. It's got loads of awesome equipment that is helping us solve these mysteries by producing loads and loads of data. And with that much data, hopefully, we are going to look deep into the universe. One of the good things about the Rubin Observatory is its telescope is really powerful, so it's going to be able to look really far away, some deep, distant galaxies, but also the dynamic universe. So how the universe changes, because different objects don't stay still the whole time. So we're going to unpack kind of the how it's going to do it, the why it's going to do it, and what it's going to use throughout this tour today. So the first main thing to talk about is the Legacy Survey of Space and Time. This is the main mission, the main thing the observatory is going to be working on. It's going to take about 99% of its time. And LSST is its name for short, which is a lot easier to say. So you'll hear that bouncing around a whole lot more than the Legacy Survey of Space and Time. And it's also what the observatory was originally called before they changed it in 2019 to the Vera Rubin Observatory. So this is basically, the telescope is going to get a 10-year time lapse of the southern hemisphere night sky. And it is a survey telescope, so it's not focused on a singular object. It's not looking at a singular star at a time, or galaxy, or asteroid. It is going to take big, wide field pictures of the night sky, and it's going to do that to create this huge map. So the whole night sky it can see, it wants to make a big map for. And this map is going to take it about 3 to 4 days. So every 3 to 4 days, it's going to scan the night sky, take an image, move on to the next section, keep doing this until it's got that map, and then it's going to start again and do that again and again and again. And over those 10 years, we're expecting it to do it about 800 times. So we're going to have 800 different maps to kind of combine together to get this really detailed image of our southern hemisphere night sky, but also see what changes between each time. And that's one of the things it really likes to do. It's going to detect changes between each map that we make. And each night, it is expected to detect 10 million changes. So that's a whole lot going on. It's going to detect the changes between each image. It's going to stack them on top of each other and see kind of the comparison, what changes. And that might be an asteroid moving across the image, maybe a star that's pulsing, it's flashing at us, or a huge star has just died and done a huge supernova explosion. It's going to detect all of these, and when it does make a detection, it is going to have told us humans within 60 seconds. It's really speedy. It's what we call real-time alerts. And that's what makes it kind of so special. It can be so quick and so efficient. And then it is looking at the southern hemisphere night sky. Unfortunately, not based here in New Zealand or Lake Tekapo. This is going to be based in Chile. And this is because it's a great place for telescopes. It's where most telescopes in the world kind of live, because it's high and it's dry. So this is a closer look at where the telescope is going to be positioned, specifically in Cerro Pachón, on top of a mountain, because there's a couple of reasons. They spent about 3 years, from 2003 to 2006, finding the perfect location. And this was it. Because it's really high. It is 2,600 meters above sea level, which means when we're looking out into space, there's less atmosphere, there's less stuff for us to look through to see the stars and the galaxies. So we've got less interference with our images. The next thing is it's dry. When you have moisture in the atmosphere, if it's quite humid, that also disrupts and changes the images a little bit. But it also means there is less chance of just rainy days, so more observing time for us to do. And finally, another important thing they have to think about is infrastructure. There is no point building a telescope this kind of intense in the middle of nowhere where you can't get electricity or people to it. So what they've done is found Cerro Pachón, which already has Gemini South and SOAR, 2 other huge observatories on there. So the infrastructure, the electricity, that is all there for telescopes, but there's no towns nearby to give off enough light pollution to affect it. So we've found the perfect place down there in Chile. If we get a bit of a closer look at the observatory itself, this is when it was still being built. But here is the main observatory itself. Our telescope sits inside this weird silvery dome, which can rotate around so we can see all angles of the night sky. But also, there's this little cute telescope here. This is the Rubin Auxiliary Telescope. It's its companion telescope. So this is a 1.2 meter telescope that was brought here from Kitt Peak in the US. And its job is to be a correction telescope. It is going to look up into the night sky and it is going to measure atmospheric transmission. So how our atmosphere is disrupting and distorting the images. To do this, it is going to stare at a little patch of really well-known stars. So we know their color and their brightness really well. It's going to keep staring at those basically the whole time. And basically seeing how their light changes, what we're observing changes. If it turns more of one color or if it dims down or anything, we need to know that the atmosphere is messing up those images. So that data gets fed into the Rubin Observatory and those corrections are made so we're getting as true an image as we can to out there in space. It's not getting destroyed by Earth here. So that's kind of a lot about the main mission, where the telescope's going to be. I have a little video here to kind of sum that all up for you guys, hopefully explain it a little bit better if I didn't quite manage that. So we're going to watch this for just 1 minute.
The universe is a dynamic place, but how do scientists spot changes in the cosmos? First, they need to know what stays the same. Every night, Rubin Observatory will capture new images of the sky. Over time, scientists combine the many images of an area of sky, producing a template image of how that area typically looks. When new images are taken, the template image is subtracted, pixel by pixel, leaving only the changes. A technique called difference imaging. Whether they're flashy like supernovae, on the move like asteroids, or pulsating like variable stars, Rubin will find about 10 million things that change every night in an epic feat of spot the difference.
Cool. So that is our little summary of the first bit. We've gone through some of the basic facts. So does anyone have any questions so far? Cool. Oh, hello.
When does it start, the 10-year timeline?
So it keeps getting pushed back. Originally, it was actually meant to be 2021, but they're now saying early 2026. They're not being specific, unfortunately, on dates. Yeah, early 2026 could probably mean until June or July, but we'll hold out, we'll see what happens. I think they're not being specific in case something happens again. But yeah, soon, hopefully. Cool, we'll carry on then, because we've learned what it's gonna do, what's its mission, but how? We're gonna look a little bit more at the hardware and the equipment involved in making this all happen. So the first thing to talk about, of course, with an observatory is the telescope. This is a Simone survey telescope. It's this kind of greeny thing here, and it is 8 meters in diameter. So that's the light collecting power, that's how wide that kind of circular bit is to collect the light in, which is pretty large, but it's not the biggest. It's not the biggest we've ever made. So that's not the reason this is so important or unique. The unique part is its new free mirror kind of system. So this new design where it uses free mirrors means it can be a whole lot faster and it can be a really powerful telescope. So once again, another little video for you to explain it a whole lot better than I would be able to.
How does Rubin Observatory collect so much light and move so fast? We combined 2 different mirrors on a single surface to make Rubin's unique 8.4 meter mirror. Light hits the outer surface first, bounces up to a 3.4 meter secondary mirror, back down to the 5 meter inner surface, and then up to the camera. This mirror design gives Rubin enormous light collecting power, but also keeps it compact and nimble, so it can cover the whole visible sky in just a few nights.
So there we go. That's why it's kind of so unique and cool at the moment. But unfortunately, this is not a telescope we get to look through with our eyes. It would be very cool, but it would also be a bit of a waste. So they have actually made the largest digital camera that we have ever built. And that is what they're sticking on the end of the telescope. So here it is up here compared to a human. And it's gonna be good. It is gonna take a really wide field of view. It is looking a part of the night sky that is this big, about 45 times bigger than the full moon. So it's a huge section of our night sky, and because it's such a big, powerful camera, it can get that in loads and loads of detail. So much so that our human eyes cannot fully see a Vera Rubin image. Our eyes are not good enough. They are dumbing down the image if we have a look at it, because we cannot see enough pixels with our eyes that these images are made of. Which is unfortunate, because it means the pretty images it's going to produce are not going to be their full glory. But it's not going to be us just staring at pictures to work out the data. Computers are going to get it first, and they're going to be able to process all of that information so we can then use to make those discoveries. So yeah, pretty big. But because those images are going to be so big, if you wanted to view it at full scale in all its glory, you would need to get 400 4K Ultra HD TVs, line them all up next to each other, and that's how much area you would need to display that full image and see all of that detail. 400 4K Ultra HD TVs. And that's a lot of information, that's a lot of data. And that data has to be split between 3 different data centers, get sent straight to the US, France, and the UK to then kind of be processed, because each night it is collecting 20 terabytes of data. I don't really know very well what these different memory kind of data things mean. So to put it into perspective, if you wanted to consume that much data, you would have to watch Netflix for over 3 years continuously. Or if you're more of a music lover, you would have to listen to Spotify for 50 years non-stop just to use up as much data as Rubin will collect in one night. There's a lot going on. It's big numbers, but it's good fun. And this is why the public outreach side of Rubin is going to be so important, because even if you got all of the scientists around the world to look through this data, we probably still wouldn't get it done quick enough. So it's going to be really fun when everyone can be exploring and observing together. There we go. So that was more of the how, the equipment we're going to use. This is the why. So what's the point? Why are we putting in all of this mechanical effort and all of this effort, basically? Well, we have 4 very important kind of parts of astronomy that we want to help solve with this 10-year time lapse of the night sky. The first thing we want to do is look at our own Milky Way. So the Milky Way, it's our galaxy, and it's not a special galaxy compared to the rest of the universe, but it's ours. So it's special to us. So we would want to know what has happened. How has it come here? So what we do know is that the Milky Way didn't start out the size it already was. Our Milky Way wasn't born this big. What happened is lots of different galaxies at different points in the last 10 billion years have combined together and then kind of got stuck together and grown bigger and bigger. And each time a new galaxy has been pulled into the Milky Way, it gets stretched out into this long kind of line, and it becomes a new spiral arm of the Milky Way. So there's loads of spiral arms happening in our Milky Way, and each of them is telling us something about the galaxy that it came from originally. But the really old ones and the ones that are really small, we don't know too much about, because they're really faint or they happened a long time ago, so we haven't discovered much. But with the Vera Rubin Observatory, it is going to look really far away. It's going to look at really faint things. And it's going to cover loads of the night sky, over half of what our night sky is as humans. So that means it can make this map of all these spiral arms in the Milky Way and get a bit more detail on, how we've got to where we are today. The second thing is a little bit closer to home. It's our solar system census. So we basically want to make a map of the solar system. We want to see what's out there to find out, once again, how it started, how our solar system came to be this way, but also to keep an eye on some interesting objects. So things like near-Earth objects that are normally asteroids come near Earth. We want to detect them early. We want to know the percentage that they might hit us, stuff like that. So if we can track as many objects as possible, we're technically going to keep ourselves a little bit safer. We have currently discovered about 1 million asteroids in our Milky Way over the last 400 years or so that we've been finding them, which is awesome. But we actually think there are tens of millions of asteroids out there in our solar system. So we haven't even scraped the surface. We think Vera Rubin is going to find loads and loads and loads more asteroids, so it is going to help us make this map protect us a little bit more from asteroids that we might not know about, but they might be coming near to Earth. Then we head all the way back out into the universe, into the side of astronomy we call cosmology, dealing with the big things like dark matter and dark energy. Let's be honest, us humans, we barely know what they are. We don't know. We've never really detected dark matter and dark energy, but what we do know is they change the universe. They shape how galaxies form, how they spread out around, how they clump together or spread apart. And we want to create this huge map of the universe where all of the different galaxies are, so that we can find out a little bit more about this mysterious stuff that ends up being about 95% of our own universe, but we can't even see it. So that's a really big, important thing as well. And then finally, the changing sky. This is my favorite part. This is us looking for something called transient events. So these are things out there in space that might happen over a couple of hours, a couple of seconds, even milliseconds. So the chance that we're looking in the right place and we're observing them is really tough. When we have these objects, maybe they are big giant stars exploding in supernova explosions. Maybe we're getting 2 black holes merging together. It's a really small chance that we're going to see them. So we don't have much data. We don't know much about them. A lot of these, we actually don't know where they've come from. We've detected maybe 100 things called like fast radio bursts, but because they're so short and they're faint, we have no clue where they've come from. So with the Rubin Observatory, watching the whole night sky and mapping it every kind of 3 or 4 nights, we're going to be able to detect those changes and see a lot more, and it all changing a whole lot quicker. So that's my favourite thing to have a look out for. Hopefully we're going to detect some new huge space explosions, but all of these are really important to different parts, different people working in astronomy. So that is our next little bit, kind of the whys and the hows. So does anyone have any questions on any of that?
You talk about the asteroids you haven't seen, so our own safety and protection. Like, you're like, okay, cool. And Armageddon happens, you know that. Well, what do? You know, like, so I say, oh, we've detected this thing coming. You know, don't look up movie, you know, whatever. Like, how does it help you? Like, you know, honestly, it's like, oh no, we know what's coming.
I mean, yeah, the first part is knowing what's coming, which I guess we just humans, we just like to know.
Yeah.
I guess at that point, if we know there's something big coming our way, the best thing we do is kind of track where it's going to hit. Do we know it's going to hit? Because if it's going to hit in the ocean, it doesn't matter. But if it's big enough, it's going to hit a city or impact a lot of the Earth. We want to know. With what we're actually going to do about it, I don't know much. I know all the science fiction kind of stuff where we shoot a little rocket off at it and put it on course. But the further away we can detect something, the more chance we do have of, I guess, saving ourselves. Because if you do send like a little rocket example at an asteroid, if you knock it off course further away, it's going to more chance of it missing us. Whereas if it's closer, we've got to put in more effort to kind of curve it around. But honestly, I don't have a clue. I'm very sorry.
Knowledge is power.
Yeah, it's not my expertise. But yeah, it's a great question. Awesome. Hello.
Is space junk and satellites a big issue with visibility?
It's not necessarily a huge issue right now. The more we're putting up there, it's becoming more and more prominent. So we do track as humans where all the satellites are. So when they do go through kind of images, like through the Rubin Observatory, when it takes an image, we do have corrections where we can just kind of get rid of that light, kind of Photoshop it out of the image, basically. But it is still going to affect us. It's causing us, you know, problems. We've got to do that process. So right now, it's not too bad. But the more and more we put up there, the harder it is going to be to do ground-based astronomy. Okay, we will carry on then, because we are now going to talk about how's it going. So I've told you what it's going to do, how it's going to do it. That's all awesome. But is it actually getting anywhere? And this project actually started and was confirmed in 2010. So it's been about 16 years in the making already. This was the top-ranked priority ground-based mission in the 2010 DECAL, which is basically, I think it was like the US government deciding what is our most important missions, what do we really want to get out of astronomy in the next decade or so. And the Rubin Observatory was number 1. So we started getting construction ready not too long after in 2015. So on-site construction and then starting to construct the camera as well. So that huge, the world's biggest digital camera is also already 11 years old. Then in 2018, stuff started to arrive. We got the auxiliary telescope, our little companion telescope, put in place. And then bigger things like the telescope mirrors arriving as well. 2020, very exciting. It was announced that first light, so the first test kind of week of taking photos, was going to happen in 2021 with operations starting in 2022. I'm sure you all know 2019, 2020, 2021, not our year as humans. So of course, this didn't quite go to plan. 2022, they then told us 2023 will be first light. 2024, we will start observing. Then again a year later, 2024, 2025. Eventually, 2025, they did manage to do first light. So in April, they spent about a week using the telescope, pointing it up at the night sky, doing different bits of kind of test runs of how we're going to observe asteroids and galaxies. And then they kind of put all that information together, those images, and they presented it to the public on the 23rd of June, 2025. And as we spoke about earlier, we're now hoping 2026, early 2026, we are going to get our first operations and the start of the telescope itself. But right now, we are going to have a look at those first light images. Because remember, of course, our human eyes, unfortunately, cannot see them in their full glory. But even with that being said, they are pretty incredible. So this is our first one. This is the Lagoon and Trifid Nebula. This is actually one of the nebulas we look at on tours every once in a while. But this is a stellar nursery. This is the part of the night sky we can look up into and see new baby stars being born, which is one of the reasons, of course, we want to have a look at it with the Rubin Observatory. These little stars in here in the lagoon, and then you can see some up here in the Trifid as well, new baby stars. But of course, we also wanted to look at it. They wanted to show off how pretty they can make their images, how beautiful it can look. Because Vera Rubin is looking in optical wavelengths, so it's looking at the light that we can see with our own eyes. So it can use lots of different colors to make these images really kind of pop, but also be true to what is out there. This image took about 10 hours observing over those 7 days, and this is about 678 images stacked up on top of each other. And this is just their kind of show-off image. The next image we're going to talk about is some galaxies. So this is the Virgo galaxy cluster. So up in the night sky, if you ever find the constellation of Virgo, when we look in that direction, there are a whole load of galaxies there. So with this image, this was also taken, I think, about over 10 hours with about 1,100 images stacked on top of each other. And here, if you find any little dots with these lines through, these are stars. That's how you're going to tell them apart. So there's a few of them dotted around like here and here. There you go. But every other little dot in this image is a different galaxy. So there's a whole lot going on here. We have two big spiral galaxies. These are what our Milky Way looks like, basically. So we like to have a look at these. This kind of line of little blobs, these are galaxies, a smaller galaxy cluster. And then up here, we have a merger of three galaxies. So they're kind of starting to share all their material and dust. They'll one day combine together. But this isn't the full image. This is, once again, the Rubin people have been nice and dumbed it down for us so we can see in more detail. This is the full image. So the one we saw was only 4% of this image. And this is two Rubin images, so two areas, two camera clicks stuck together. And the part we just zoomed in on, this part up here. So we can see those two spirals and this kind of group and this merger of three galaxies here. We looked about at that square there. But this whole image is, I think we think about 10 million galaxies. Every one of those little dots, we can't even see all those little dots, remember. There's so much going on here. So yeah, and we can put some labels on this because we do know about some of these things. We've looked at this part of the night sky a lot. But every little dot, every smudge that does not have a label is because we have never found it before. We've never seen this galaxy before, or we've never had enough information to study it. And as you can tell, there is not 10 million labels on there. There's a lot just in 10 hours that the Vera Rubin Observatory has found that we didn't know existed beforehand. So far, this first light has gone pretty well. They've proved their worth quite a lot. But there is one final part to this first light, and that is having a look at asteroids. Because remember, we want to work out what's in our solar system. So I've got another video for you guys. This one is going to kind of show us how they find the asteroids and then show us a map of the asteroids they found during that first light. About 10 hours again of observing over 7 days. So, in 10 hours over 7 nights, the Rubin Observatory detected about 4,000 total asteroids. Over half of those, so 2,104, were completely new detections, asteroids we'd never seen before. With about 2,000 of them being in the main asteroid belt. So on that video there, those were the teal kind of blue colored ones just going all in the same direction along the screen. We found 7 near-Earth objects, 11 Jupiter Trojans. These are asteroids that share the same orbit as Jupiter, so they're a little bit further out than the asteroid belt, and then 9 trans-Neptunian objects. So these are the ones that are beyond all the planets. They are in the Kuiper belt, the Oort cloud, the really edges of our solar system. Things ridiculously faint, ridiculously small and hard to see. So it did a good job once again in just 7 days. I want you guys to have one more look at the video because we're going to spot the different colors to find those different types of asteroids. So the teal ones, they were the main asteroid belt. You will find some purple ones that are moving really slowly across the screen, like here. These are the trans-Neptunian ones, really far away. We have some blue ones, are the ones around Jupiter, and then these little yellowy orange ones are our near-Earth asteroids, the ones moving completely different, really fast across the view. And of course here we are getting to see the little section of the night sky that Rubin observed, but it is going to have the chance to observe this whole circle and observe so many more. So we think in the first year of the Rubin Observatory that it is going to detect more asteroids than we have ever known about before, just in the first year. So yeah, loads going on there. Okay. So, does anyone have any questions about our first light stuff and what's been going on so far?
Hello.
Hello.
What does the different colors in the first light image mean?
In which one, sorry?
The first light image. What do the different colors mean?
In which of the images?
The first light image.
Do you mean, oh, sorry. This one here? Yeah. So this is kind of different things giving off different light, different elements. So these big clouds here, they're going to be mainly made of like hydrogen and helium. And when they give light off in space, they do actually give it off in certain colors. So you'll also notice some of the stars are whiter or more red. Those are the different star colors as well. But when we look out into space, different clouds of material and stuff, depending on what they're made of, will actually emit different colors. It's not what we can see with our eyes, because our eyes are not as good as cameras. But this is actually what it looks like if you manage to get big photos. Cool. Awesome. There we go. So the last little thing I want to do is just show you guys these 2 websites, because they are going to be one of the ways you can keep up easily and in a fun way with what is going on with the Rubin Observatory. So our first one is called Sky Viewer, and it is basically a huge map. It's that map of the southern hemisphere night sky that Vera Rubin is taking. So at the bottom, you're going to find out what field of view we are compared to the Rubin Observatory. So if we zoom out, we may recognize this little section here. This is what we were looking at earlier, that first light image of all the galaxies. And then we zoom out, and this is all of the rest of that image. So 2 Vera Rubin photos stuck side by side. And it basically means you guys can zoom around, have a look in, learn more, a little bit more about those galaxies. And as more parts of the night sky, once it starts, it'll get added on in kind of like these black mysterious bits here. So you can kind of watch this build up over the 10 years.
So this is like Google Earth, but for space.
Exactly, you've got it.
Google Earth, but the other way around.
Yes, unfortunately only for the southern hemisphere night sky. So if you guys are up from the northern hemisphere, the parts of that night sky like Ursa Major, the Big Dipper, the Little Dipper, the North Star, they're not going to be in these maps because Vera Rubin cannot see that side of space. But yes, Google Earth, but for space. I like it. And then the next one is called Orbit Viewer, which does a pretty similar job, but it's with our asteroids that we've found. So if we just give it a second. No. There we go. So this can now show us all of the asteroids. So what we're looking at right now is kind of a sample of all the asteroids humans have ever discovered. This isn't just the Vera Rubin right now, but it has mapped them, and we can change time, speed it up, and we can watch how they all rotate around the sun, which is just in the middle. We've got labeled some of the interesting planets, some random asteroids, and the colors are a little bit different this time. So the pink are now the asteroid belt. But if we want to look at just the Rubin Observatory ones, we can go into filter. And these are all those 4,000 detections that it made for those 10 hours during first light. We can see how they've really moved around in the last year since those photos were taken. So this will build up more and more detections will be added as the observatory does its stuff. But yeah, there's loads more for you to explore. I've literally just shown you the basics on these. There's different tours that you can do. So they've set up pre-programs to kind of give you facts and fly you through the images and stuff. So I recommend having a look at those. And for the sky viewer, there's a listen one. So you can set a little dot along the image, and depending on what galaxy you're in, it'll give you a different sound. Sounds really weird, but it's very relaxing background music. And yeah, you can change all of these. We can have a look here at which objects we want to see, like the near-Earth asteroids and normal asteroid belt. So I recommend going and having a play around with it at home as well. But that is kind of one of my final things to talk to you guys about. I have a couple of final kind of numbers, which are going to be nice big numbers to blow us away at the end. And this is, as we said at the start, there are going to be 10 million detections per night with the Vera Rubin Observatory. So much data, and it is going to collect more information and more data in just the first 1 or 2 years than every other optical telescope has before combined. So in just 1 or 2 years, it's going to give us more data than we've ever had on the universe and how we can see it. We are overall going to detect about 20 billion galaxies, we think, in that 10 years. We think about 40 billion celestial objects, so individual stars and galaxies, maybe some planets as well. And then finally, we will detect, as we said earlier, more asteroids in the first year or two than we have ever known before. And we've been looking for asteroids for about 200 to 400 years. So in 1 year, detect more than we've found. It's going to be pretty fun. So my recommendation is to just keep your eyes out on the news over the next year or so at this telescope. This is a great time for you guys to have joined me tonight and learned about the observatory, because we're so close, hopefully, early 2026. But we're going to finish with this quote here, which is, "Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies." And this is from Vera C. Rubin, who was an incredible astronomer that the telescope is now named after. She was a pioneer in discovering and learning stuff about dark matter. And that's why, with that being such a big part of the mission in 2019, they decided to name the observatory after her. And I think it's a great quote. It sums up what we're going to do with this telescope. So thank you so much for joining me tonight, guys. It's been great to have some time with you and have all your great questions. If you guys want to learn a little bit more or look at those sky viewers and orbiter viewers, those QR codes are there for you. But thank you very much. Yeah, I will turn the lights up a little bit now. And yeah, thank you.
Thank you.